Welcome to ATMOS 5000, day number 26. Our objectives are being pulled from Stull, Chapter 15, sections 15.3 and 15.4. And today we're going to investigate as much as we can about lightning and tornadoes. So lightning flashes over the United States are actually measured using the Vizsla National Lightning Detection Network. This network was privately funded by the U.S. insurance industry in order to try and diagnose insurance fraud, because if your house burned down and you claimed it was hit by lightning, they could look at the National Lightning Detection Network and say, oh, sorry, there was no lightning within 100 miles of your house, therefore it must be arson and we're not going to pay for your claim. So, but if you look at the long-term kind of climatology of lightning from the National Lightning Detection Network, you'll see that it closely mirrors the air mass thunderstorm distribution, with the highest concentrations of lightning flashes along the Gulf Coast, specifically in Florida and Louisiana, with a secondary maximum in the eastern Oklahoma, southern Kansas, associated with the supercell thunderstorms. And of course, not much lightning in the west because you're missing the moisture associated with the lift instability and moisture requirements for thunderstorm formation. If you look at lightning flash rates from satellite around the globe, and not just in the United States, you'll see that there's a very distinctive pattern where lightning flashes are much more common over land masses than they are over the oceans. And the satellite network basically has determined that there's more than 100 cloud-to-ground lightning strokes per second are occurring worldwide. The most frequent lightning flashes occur in Central Africa, and there's a secondary maxima in South America, in Argentina, and then there's also up near Venezuela. In the northern part is one of the most active lightning regions in the world. So what makes the light and noise associated with lightning and thunder? Well, the lightning flash is associated with the flow of an enormous amount of electrons along a path of least resistance through the atmosphere. And these air molecules are excited to a very high temperature as a result of the electron flow. And the bolt of lightning is generated by that heat, and it's actually as hot as the surface of the sun, which leads to visible light being generated. And then that enormous amount of heat causes the air to rapidly expand, which causes a pressure wave, which we experience as thunder. So how is thunder produced? Well, lightning heats that air to 30,000 degrees Celsius, which causes the air to rapidly expand by a factor of about 100. And those expanding air molecules collide with one another, creating that pressure wave, and that pressure wave travels at the speed of sound, which is about 1 mile every 5 seconds. So propagation of thunder. So the sound of thunder depends upon the orientation of the lightning strike, and it also depends upon the location of where you're at. It can also depend upon the thermal structure of the atmosphere. So for example, we have a person over here on the very left of this, very near the lightning strike, and they claim that the lightning sounded like a bang. They were hit directly by the pressure wave without any length of time extending between the lightning flash and the sound of thunder because they were so close to it. As we're further away, the middle person in the middle part of the screen, they experience the thunder as a rumble. The reason being is that they are hearing different pressure waves from different parts of the lightning flash arriving to them at different times. So the part of the lightning flash that was occurring up near the cloud takes a little bit longer to get to them than the one that was actually near the ground, and intermediates all the way in between. And then you also have some bouncing off of the sound waves of surroundings. And so they get a rumble. And then the other thing about the atmosphere is because the atmosphere is normally stable due to the environmental lapse rate, the sound waves are actually refracted upward in the atmosphere. So if you're far enough away from the lightning flash, the sound waves will actually pass over your head. And that's what's happening to the person way over on the right, and where this says nice flash but no thunder. That person would experience what we call heat lightning, where they essentially see the lightning flashes, but they don't hear the thunder associated with it. So why do we need to worry about lightning? Lots of reasons. Well, if you're hit by lightning, it can directly burn your skin and your hair or your clothing. It can cause hemorrhaging, internal bleeding. The most damaging part of it is the fact that being hit by lightning can cause your heart to stop beating regularly. It can go into an arrhythmia, or it can tear your aorta. And of course, if your heart stops beating, you don't have very long to live. It's also possible to get mechanical blunt force injuries due to falls or being blown away from the lightning stroke. If it happens to hit you in the head, it can cause internal bleeding inside your brain, which would be very not good. It can cause other internal organ failures depending upon the path that the electricity travels through your body. Many people suffer major eye damage from the lightning flash and form cataracts within a few days. And the high pressure shock wave from the thunder can basically rupture people's eardrums along the way. So lots of damaging things can happen if you're hit by lightning. It's a good thing to avoid. So how many people die from lightning strokes each year? Well, if you look over this 10-year period between 1997 and 2006, or a 30-year period from 1997 to 2006, you'll see that lightning kills on average between kind of 40 and 60 people a year. And that's more than about comparable or slightly more than die from tornadoes or wind or winter storms, all those sorts of things. Flooding typically kills more people than lightning, but it's still not an insignificant number. What's interesting, however, is that 84% of all lightning victims are male, and I'll leave it to you to make your own explanations for why that might be the case. So if we look at the fatalities in this 13-year period between 1990 and 2003, with the top panel is looking at the number of fatalities, the raw number in each state, and the bottom panel is looking at the rate of fatalities when normalized to the population of the state. So if we look at the raw fatalities, most of those, the largest number, occur in the southeastern United States, Florida, Texas, Louisiana, Alabama, Mississippi, and Georgia, down in that region. And that makes sense because that's where the thunderstorms are most frequent. But you'll also see a secondary maximum in Colorado and also in Utah a little bit. You'll see 22 people died during that time frame. If you normalize it for the number of people that live in each state, then you have hot spots down in Florida and Louisiana and Alabama, but then you have the Rocky Mountain states, basically all the way from New Mexico all the way up through Montana and Idaho and everything in between. So it's something that we definitely have to pay attention to in the Intermountain West. So what's interesting is we know a lot of things about the atmosphere. One of the things that we do not understand very well is how lightning is initiated within a thunderstorm. It's extremely difficult to make measurements that are necessary to constrain the lightning issue. And it's even more difficult to model because we're not sure that we even understand all the processes that are involved in the formation of lightning. This is a really interesting 5-minute video that's a snippet from a NOVA special, which highlights our lack of understanding of what initiates lightning and basically puts forth a new theory onto what generates the actual lightning bolt. And basically it looks at how cosmic rays, rays coming from outside of the Earth, may be important triggering mechanisms for lightning in our atmosphere. And I encourage you to follow the link and watch this 5-minute video. It's really kind of fun. And then I also encourage you to watch this other 5-minute video from the National Geographic that follows basically some of the work of Tim Samaras. He's a very famous meteorologist who was a very famous storm chaser. He was one of the first storm chasers to actually put an instrument package in front of a tornado. He was an electrical engineer, and his specialty was actually building high-speed photography, and has some wonderful views of what lightning actually looks like at 100,000 frames per second. Unfortunately, Tim Samaras was killed by the largest tornado that's ever occurred during one of his scientific expeditions. So the world is made up of conductors and insulators, and it's important to know the difference when you're talking about lightning. So materials which allow electrons to flow easily from orbiting around one atom to another are good conductors. And materials that inhibit these electron flow are good insulators. So air is a very good insulator and consequently a very poor conductor. Rubber is a good insulator and a poor conductor. And metals are the opposite. They're very poor insulators, but very good conductors. And water, of course, is a very good conductor as well. So in the atmosphere, we have a fair weather electric field. So we could go out and we can actually measure the strength of this electric field that exists naturally in the Earth's atmosphere. So in clear air, the atmosphere has this net positive charge and the Earth has a net negative charge. And thunderstorms are responsible for depositing electrons on the Earth's surface and removing electrons from the atmosphere. And we believe that this fair weather electric field is maintained by the nearly constant lightning flashes that are occurring around the globe. Remember, there's more than 100 cloud-to-ground strokes of lightning every second, as measured by satellite somewhere on the globe. We have some theories on how clouds actually separate charges, and one of those theories is the interface charging mechanism. And what we have here is you can think of this as an ice crystal or an ice bar or whatever you want to do, but let's just say that there's a temperature gradient across this ice. And you have a warm part of the ice and a cold part of the ice. Well, the warm part, the molecules are more energetic and are able to move around a little bit faster. In this case, the electrons, which are lighter than the protons, are more mobile. And they will migrate away from the warm section and will basically end up at higher concentrations in the cold part of the ice rather than the warm part of the ice. And so by having temperature gradient across the ice, you can actually get charge separation within the particle itself. That's the first step. These temperature gradients in ice result in charge separation, yes. So the second step, let's say that we have a Grapple particle, and these super cool droplets, denoted by green here, are freezing on contact. And when they freeze, they release latent heat. And what's that going to do? It's going to warm up the exterior of the Grapple particle. And so now you have a temperature gradient inside the Grapple. The outside of the Grapple particle is warm. The inside of the Grapple particle is cold. And so you have this net migration of electrons, which are more mobile, away from the warm spots on the ice and into the cold interior of the Grapple. And that leaves the outside of the Grapple positively charged. Step 3 of the interface charging mechanism has to do with the interaction of this Grapple particle along with ice crystals in the atmosphere. Now, I know that I have shown the ice crystal here as a 5-sided star, and hopefully you'll laugh about that a little bit because we know that ice crystals are in fact 6-sided objects for the most part, hexagonals, but just bear with me on this one. I just wanted to differentiate the Grapple away from the ice crystal. And so we have this ice crystal, and this ice crystal, recall, is being exposed to the fair weather electric field in the atmosphere. That fair weather electric field, remember, has positive ions in the atmosphere and negative ions on the surface. And recall that the opposite charges actually attract one another. So what happens is that these ice crystals will tend to align themselves with the fair weather electric field in the atmosphere. And so you'll end up with a net positive charge on the bottom of the ice crystal because that's being attracted to the negative charges on the Earth's surface. And that leaves essentially a net negative charge on the top part of these ice crystals because they're being attracted to the positive charges in the Earth's atmosphere. And this graupel, of course, is going to be falling faster than the ice crystals. And if they actually collide, this is not like the supercooled droplet interaction. These are ice crystals. They're already frozen. And what they'll do is they'll tend to bounce off. But when they touch each other, that electron is more mobile than the protons. And when these two things touch each other, the ice crystal will donate its electron to the graupel, and it will lose that electron and it'll bounce off. And so at the end of this scenario, the ice crystal will be positively charged and the graupel will be negatively charged. So we had the collision, and then there should have been a negative transferred to the graupel, and the ice crystal should be positive now. So there's another way that you can have a transfer of energy called the induction charging mechanism, and this one is making use of the fair weather electric field in both the ice crystal and the graupel particle. So now you don't have to have a temperature gradient across the graupel particle in order to separate charges. You just happen to have it exposed to the fair weather electric field, and it will end up in the same orientation as the ice crystal. And when these two things touch, once again, there'll be a transfer of an electron from the ice crystal to the graupel. The graupel will become net negative, and the ice crystal will become net positive. So charge distribution and charging mechanisms in thunderstorms. So what you have is you have these ice crystals that are small, and they can easily follow the updrafts, and they're positively charged. They will end up accumulating those positive charges in the upper regions of the cloud. And the graupel, since it has a higher terminal fall speed and it's negatively charged, will start moving down. And so you end up with this charge separation in the clouds where you have accumulation of negative charges in the lower part of the cloud and positive charges in the upper part of the cloud. And what will happen is underneath the ground charges will migrate, being attracted to the opposite charge in the cloud itself. So underneath the cloud, you'll have positive ions that are attracted to the negative ions in the cloud, and underneath the anvil, you'll have negative charges on the ground that are being attracted to the positive charges in the anvil. So we have charges positive in the upper part of the cloud, negative down below, positive on the ground under the cloud, and negative underneath. So the lightning stroke itself, 80% of all lightning strokes occur in cloud or cloud to ground, which means that only 20% of them actually are cloud to ground. So that's probably a good thing considering what's going on in California right now with all the fires. A lot of those were caused by lightning, cloud to ground lightning strokes. The lightning stroke actually consists of about 4 different events. The first event is the step leaders, which are emanating from the bottom portion of the cloud. Then once those step leaders get close enough to the surface, we can have a traveling spark and initiating the return stroke, which is actually the visible light that we see associated with the lightning stroke. Then we can have a dart leader, which instead of taking a whole bunch of steps to make the bridge the gap between the cloud and the ground, can make the leap much faster because there's already a conduit between the cloud and the ground. And that would then be followed by a second return stroke or more return strokes. Let's take a look at these in a little more detail. So here we happen to have a cloud that has charge separation, positive in the upper part, negative in the lower part. We have positive charges on the ground, which are being attracted to the cloud. And then we have a series of step leaders where those electrons that are mobile are being attracted, and they're trying to follow the path of least resistance down to the ground. And so the thing that they're doing is they're trying to find the easiest path down. So they're trying to find a conductivity path and also find something that's tall so they don't have to go quite as far. In this case, it's just denoted as a church steeple, but it could be a tower or anything else. It doesn't really matter. If the object on the ground is conductive and pointy, then it's likely to be hit by lightning over time. These step leaders are each about 50 meters long and take just a few microseconds to actually move that distance. And then once the step leader gets close enough to the object on the ground, then you can have a traveling spark which travels from the ground to the step leader, completing the circuit, at which point you will have a return stroke. In this case, you can see visually, you can see all of the step leaders coming down, and then you have this bright central stroke. That is the return stroke, and that is essentially traveling from the ground upward. I know we all think that lightning comes from the sky down. The step leaders do, but the step leaders are kind of subvisible. They are too fast and are too faint to actually catch with your eyes, but we definitely see the return stroke. It's hard to see the step leaders, but the return stroke happens so fast, it is in fact moving up. And so here we have the completion of that circuit, and we have the return stroke moving up to the cloud. So the lightning stroke itself. That was called a negative polarity strike. You can also have a positive polarity strike, which is lightning that is occurring between the anvil and the negatively charged ground underneath the anvil. Now, because these two charge centers are separated by further distance, you have to have a larger charge separation in order to generate the lightning stroke in this region, which means that these positive polarity strokes are less common, but they're also much more powerful than the negatively charged negative polarity strokes that are more common. We can also have what we refer to as a bolt from the blue, where you actually have lightning that is traveling horizontally away from the cloud before coming back down to the ground. What it's essentially doing is it's trying to follow a path of least resistance, and it may be following air that was ionized by previous lightning strokes, or air that happens to have slightly higher than normal vapor concentration. And needless to say, it is possible for this lightning to occur outside of the area that is underneath the cloud, and we refer to that as a bolt from the blue. Lightning safety. This person is experiencing a very strong static electricity charge. If you are outside and you feel the hair on your body tingle with static electricity, that is a warning sign that you are about to be hit by lightning, that you are in that area of charge buildup on the ground, and you definitely do not want to be the highest thing around in that scenario. So you have to take immediate action or risk being hit by lightning. Here I introduced the 30-30 rule for lightning safety. It basically says that if you see the lightning and you can't count to 30 before hearing the thunder, you need to basically go inside. And it's best to stay indoors for 30 minutes after you hear the last clap of thunder. The first one, since lightning travels 1 mile every 5 seconds, basically says that you need to go indoors once lightning is within 6 miles of you, and that's the safe and prudent thing to do. And the picture here is actually a bolt from the blue. You actually have a lightning stroke coming out the side of the thunderstorm and coming back to where the storm had already passed. And that's one of the reasons why you want to stay indoors for 30 minutes after hearing the last thunderclap. And here's an example of the crazy things that lightnings can do. This lightning was moving along horizontally and then ended up coming cloud to ground eventually, sort of thing. So lightning is very unpredictable. So these lightning safety rules, If thunderstorms are imminent, basically postpone your outdoor activities and come back a different day. It's best to avoid being in a dangerous situation. It's better to move into a building or inside a car. Cars are generally safe, but if you feel the static electricity buildup and you're next to your vehicle, I'm not sure that I would try and open the door and get in because you're in imminent danger of being hit. You need to take immediate cover, and touching your vehicle may not be the best thing in that scenario. Where you do not want to shelter are in small sheds or small metal sheds under isolated trees or in convertible automobiles. And you definitely want to stay away from tall objects, especially if they happen to be pointy and especially if they are conductors made out of metal. If lightning is occurring and you can't get to a building, you can get into the car, but try to avoid touching any metal. And of course, these utility lines and metal pipes can conduct electricity. So even if you're inside, it is possible to be hit by lightning. The more common ways that people are hit by lightning on the inside is taking a shower or talking on a landline telephone that is literally connected to wires outside the house through wires inside the house. And if you're outdoors and there's no shelter nearby, you definitely want to find a low place away from high things, away from trees and fences and poles. And if you're in the woods, take shelter underneath the shorter trees. And if you feel that tingling sensation that you're about to be hit by lightning, you want to squat down on the balls of your feet to minimize your contact with the ground. Make your back as round as possible and place your hands over your ears and head. Because if the lightning is really close to you, it's going to be really loud, and you want to basically kind of close your eyes because you don't want to expose yourself to the lightning flash itself. And so you're really trying to make yourself to be as small as target as possible, but definitely do not lie down, because once that lightning hits the ground, it will spread out on the ground. And if you're laying prone, then the chances are you might be hit by one of those stray sparks, basically, moving through the ground. And if you're boating or swimming, get out of the water. You do not want to be the tallest thing in the water, and water is a great conductor of electricity. So if you're in a swimming pool and anywhere on the swimming pool gets hit by lightning, you will be electrocuted as well. So here we go. What happens when lightning hits objects? Well, this tree was lucky. It has a lightning channel down the trunk to the ground. What often happens with these trees is they get hit by lightning and it heats up the sap inside the tree or the water inside the tree, flashes it to steam, which causes a rapid expansion of the volume, and we can actually blow the trees apart. And that's what you see here. This tree was literally split wide open by lightning striking it. And of course, there's shrapnel that can be expelled from this type of explosion as well. Here we have lightning that struck a tree and then traveled along an underground pipe. And as it did so, it caused water in the soil to flash to steam. And you can see that it actually ruptured the surface. So lightning definitely loves to travel along a path of least resistance, even if you can't see what that path might be. Here we have lightning that actually struck a flagpole on a golf course. And you can see that the electricity, once it hit the flagpole, it spread out along the surface. And that's why you don't want to lay down on the surface, because here you can see that that lightning is actually spreading out, that electricity is spreading out, and by minimizing your contact with the ground, you minimize your chances of being hit by one of these channels. This is why you don't want to be near fences, especially metal fences. So in this case, the fence was struck someplace far away, but electricity traveled down, and these cows had their heads through the fence, basically munching on grass on the other side, and it electrocuted them all, and now they're dead. The other thing that cows often do is they like to huddle underneath an isolated tree when it starts to rain, which is great, except for when lightning hits the tree, it can kill the cows. So my advice to you is don't be a cow. You're smarter than that. Avoid conductive objects and isolated trees during a thunderstorm. Fishing is also a bad idea in a thunderstorm. This was a carbon fiber fishing pole that got hit by lightning, and you can see that it just completely trashed the pole. So definitely pretty scary event. The lightning can also travel through metal pipes and sort of thing. In this case, it was traveling through a concrete, and there happened to be water in the concrete, which was then transferred or caused to flash to steam. And as it did so, it actually blew the concrete apart. So the lightning that hits outside, if there are wires, electrical transmission wires, that electricity can then pass into your house and come out in strange locations. This one happened to burn out the electrical socket in somebody's garage. Here's an example where electricity came in and burned out the wiring and a switch in somebody's kitchen. And this one, the lightning actually came out of the electrical socket in the bathroom and destroyed the mirror inside the bathroom. So we have recently, in the last 20 years, discovered different types of lightning that are occurring above the thunderstorm, typically between the top of the troposphere and the mesosphere. And so here we have a thunderstorm that's extending to the top of the troposphere, and you can see that we have the negative polarity lightning underneath the thunderstorm and the positive polarity lightning ending up out underneath the anvil. But we also have blue jets, which are above the core of the thunderstorm. And we also have red sprites, which can occur over the anvil. And then we have some other ones that we'll talk about, elves, and more recently, gigantic jets were discovered, as well as gnomes and pixies and trolls. But we're only going to talk about some of these because these are really new discoveries, some of them are. So let's talk about red sprites. So red sprites are large, brief, and often highly structured bursts of light occurring above thunderstorms, and they are in response to cloud-to-ground lightning flashes. And a single sprite can span altitudes from 40 kilometers all the way up to 80 kilometers. So this is definitely happening in the stratosphere and mesosphere. These sprites last for several milliseconds to several tens of milliseconds, and they're long enough to just barely be perceptible to the human eye. And they tend to occur above strong positive polarity strikes in the anvil. So here is a video of red sprites. It's one of the best videos that I've ever seen. So let's go ahead and play that. So there you can see, at this high-speed photography, that we do, in fact, have these red sprites that are occurring above this particular thunderstorm. So here's another amazing example. This is taken down in the Andes, where the thunderstorms are actually on the other side of the crest of the Andes, and so it looks like clear skies. But it's a perfect venue to take pictures of the red sprites. And so you have these red sprites with these tendrils that are going down that are often blue. And pilots were the first people to actually see these things. And they said, that they called them red jellyfish with blue tentacles. And you can kind of see why. But pilots were very reluctant to talk amongst themselves about these sorts of things because they were just barely perceptible. And actually, one of the things that they did to verify their existence was talk to some of their astronaut friends who were able to actually witness these things from above on the International Space Station to verify that they were in fact real. Next, we have our blue jets. So blue jets are associated with an upward directed lightning shooting out of the tops of these clouds. They have blue starters, are small and extend only a few kilometers up, and blue jets extend much further, all the way up into the stratosphere at around 40 kilometers. They occur relatively frequently, around the same rate as sprites, And these gigantic jets, which reach as high as 80 kilometers, are, on the other hand, very rare. And all of these jets are occurring directly over the thunderstorm core. So here we have a video of blue jets in action. ELVs are these rapidly expanding rings of predominantly red light centered above the cloud-to-ground lightning stroke. These ELVs expand outward at the edge of the ionosphere, typically 80 to 90 kilometers up in the mesosphere, and can attain diameters of 300 kilometers in less than a second. These ELVs cannot be seen with the naked eye, and it took specially designed photometric imaging instruments to be able to see these ELVs. And actually, if you have the special equipment, these are the most frequently occurring type of exotic lightning on the planet, and they occur at a rate of about 3 ELVs per minute over the planet. So here we have, essentially looking at what we were seeing, we have the stratiform region of the anvil with the positive cloud-to-ground lightning strokes with the Sprite and its tendrils above that, with the ELV occurring above the Sprite. We have our upward directed blue jet coming out of the top of the core of the thunderstorm as well. Ball lightning is a very rare phenomenon described as a floating illuminated sphere that occurs during thunderstorms. It's been exceedingly hard to get video or data on what exactly ball lightning is, but we do have plenty of eyewitness accounts. And it can be described as very fast-moving or slow, stationary. It can be quiet or can produce a hissing or crackling noise, and it can pass through windows. It can last from several seconds to several minutes, and can disappear slowly or suddenly, either quietly or with a loud bang. So obviously it presents itself in a lot of different ways.
Lyons, Colorado, June 2001. Is it a firefly? Is it a plane? Is it a UFO?
There were 2 really bright lightning bolts. And then right in the middle, for about 10 seconds, there was this glowing ball of light. We never seen anything like that.
It seems to be a rare and mysterious phenomenon called ball lightning.
Nobody knows what ball lightning is. I mean, understanding normal lightning is difficult enough, but ball lightning is something entirely different.
Yet it has been seen by thousands of people all over the world, and their descriptions are strikingly consistent.
Most people describe ball lightning as being about the same size and brightness as a 60-watt light bulb. So suppose you're sitting in your living room and there's a thunderstorm outside. You look out your window and you see this floating along outside your window. You then see it comes through the glass into your living room, approaches you, and then suddenly either exploding or quietly disappears. That's how people describe ball lightning.
And then this is the first observation of ball lightning that has been published in the literature. They actually were able to capture ball lightning here on the left, and they were actually able to do a spectrographic analysis to see what colors the light were, and from that you can actually determine the temperature of the ball lightning as well. So St. Elmo's fire is another type of phenomenon. It's an electrical weather phenomenon where you have these bright blue or violet glow that kind of looks like fire, and it emanates from tall, sharply pointed structures such as lightning rods, masts, spires, chimneys, or on aircraft wings and propellers. And often accompanying the glow is a distinct hissing or buzzing sound. And I love this picture. This happened to be a picture taken in the cockpit of an Airbus jet that was flying over the ocean. And it happened to have a wonderful example of St. Elmo's fire occurring on the front of the aircraft at night. We're now transitioning from talking about lightning to talking about tornadoes, but I just want to contrast tornadoes with hurricanes, cyclones, and typhoons, which are a much, much larger storm that form over tropical oceans. These storms tend to last about a week with sustained winds between generally 75 and 175 miles per hour, although the strongest hurricanes have had winds over 200 miles an hour. And we categorize the strength of these storms using the Saffir-Simpson scale between Category 1 and Category 5. If you live in Utah or any other place in the West, you will become very familiar with these dust devils. These are not tornadoes. These are approximately 10 meters wide and a kilometer tall. They form over hot, dry regions during the day. They generally last less than 30 minutes with winds of less than 75 miles an hour, and they have been observed on the surface of Mars, so it's not just an earthly phenomenon. And of course, these are your tornadoes. Tornadoes come in lots of different sizes, lots of different shapes, lots of different varieties. The top one here is a relatively small, nice-shaped funnel tornado that has a debris flow of about 100 meters wide at the surface. And the one below at the bottom has a funnel which is almost 1 mile wide at 1,500 meters. They generally form from supercell thunderstorms, although they can also form from multi-cell thunderstorms or mesoscale convective systems. They generally last less than 1 hour, and the maximum sustained winds range between anywhere about 75 to over 300 miles an hour, and they are in fact the strongest winds on Earth. If you look at a map of where tornadoes occur around the globe, you'll notice that by far North America, and specifically United States, is the tornado capital of the world. Africa has almost no tornadoes. Much of Asia has almost none. Other hotspots are kind of New Zealand, Japan, Bangladesh, parts of Australia, and parts of Argentina. And you ask yourself, why is this the case? Well, it actually happens to be basically resulting from unique geography. So why is the U.S. the tornado capital of the world? It's really one of the only places in the world where you have a north-south trending mountain range that funnels warm, moist air from a warm body of water to the north, and funnels cold, drier air from an interior continent down to clash with that in terms of a cold front. But what makes us unique is that we also have an elevated desert plateau to the west. And that brings in hot and dry air, which can act as a capping inversion and a dry layer above. And so you get all of those ingredients for a supercell thunderstorm: lift, instability, moisture, boundary shear, capping inversion, and dry layer. LIMS CD. So if we look at tornadoes in the United States, this is the number of tornadoes each year in a 10,000 square kilometer box. So that's in essentially a 100 kilometer by 100 kilometer box. And you'll notice that Oklahoma has between 15 and 20 tornadoes in that 100 kilometer by 100 kilometer box each year. You'll also notice that Florida has a high number of tornadoes as well, but a lot of these are actually classified as waterspouts, which are very weak tornadoes that often occur with air mass thunderstorms and are not the dangerous and deadly variety that are associated with supercell thunderstorms. So what month do tornadoes typically occur? So here we have the different categories of tornadoes between F0, which is the Fujita scale, being the weakest tornado, all the way up to the F5, which is the strongest. And you'll see that the dominant tornado months are actually April, May, and June, sliding over into July a little bit as well. But the most dangerous and deadly F4 and F5 tornadoes are almost exclusively kind of in that March, April, May, June time period. What time of day do these tornadoes generally occur? Well, because a lot of them are driven by surface heating, and a lot of them come from supercell thunderstorms that have to have enough energy to punch through the capping inversion and the dry layer. most of these thunderstorms spawn their tornadoes late in the day. In the evening, 3 to 7 o'clock at night local time. And you'll notice that the dangerous F4 and F5 tornadoes almost all occur exclusively during this time. Although there are a small subset of tornadoes that can occur any time of the day, even 4 or 5 o'clock in the morning. But those would require, generally speaking, a different lifting mechanism than surface heating. It may be frontal lifting that may be the driving factor on those tornadoes. So how do tornadoes form? Well, if you have speed shear or wind shear with height, you'll know that it will generate horizontal rotation in the Earth's atmosphere. We've seen that before, the spinning of the pinwheel. But if you have an updraft underneath that horizontal vorticity or the horizontal rotation, it will tilt that rotation into the vertical. And now you have a supercell thunderstorm that has a part of it that's rotating clockwise and a part that's rotating counterclockwise. And we've already talked about storm splitting and how one of those types of thunderstorms will split off from the other and will be preferential and will persist. So generally speaking, in the northern hemisphere in the United States, 90% of all these supercell thunderstorms that generate tornadoes are rotating counterclockwise, and thus the 90% of the tornadoes are rotating counterclockwise. Once you have that rotation tilted into the vertical, then we have a process called vortex stretching, which intensifies the rotation and reduces the pressure at the surface. And the last step is the funnel becoming visible due to condensation and or debris. So here we have an example of a wall cloud on the left. That wall cloud is hanging down underneath the rotating mesocyclone. Over on the right, we have a tornado. The funnel cloud is what you see at the top. It's being illuminated by the sun. And that is the condensation that's occurring in the low pressure inside the tornado. And that is coming from the wall cloud itself. But on this particular day, the lower part of the atmosphere is not moist enough for this funnel to extend all the way down to the ground, yet it's clear from the debris that's being picked up on the ground and being lofted that this is in fact a tornado with rotation on the ground, even though the funnel cloud itself does not extend to the ground. That is not a requirement for a tornado. But here's an example where you do have a funnel cloud that extends all the way to the ground, but people are often misled by assuming that the funnel cloud is the width of the tornado. The funnel cloud itself is the central part of the tornado where the pressure is the lowest, but the tornadic winds can often extend quite a distance away from the internal funnel cloud that you see. And this picture dramatically illustrates that you have a very wide tornado with a very small central funnel. And so the tornado is the width of the debris and not the width of the funnel cloud. So here we have a computer simulation of a tornado. The contoured colors are pressure perturbations, with blue being the lowest pressure. And then we have a series of tracers, the green dots, which are going to get sucked into the tornado, and you can see how they respond to the pressure perturbation and the winds inside the tornado. So when it comes to tornadoes, size matters a lot when it comes to wind speed. So here we have a very large tornado, a little more than about 1.5 kilometers wide. And it's hard to tell where the cloud stops, where the funnel begins, because it all gets kind of mushed together and where the debris starts to flow. So here we have an image of what we call a rope tornado. This happens to be illuminated by the sunlight, so you can see the white cloud inside the funnel itself. You can see that it has a debris field, which is much bigger than the funnel, and it also happens to have a rainbow there. It's kind of a really nice little picture showing the death and destruction, but the beauty as well. Here we have a rope tornado that is basically getting left behind by the cloud. The cloud is moving faster than the tornado is at the ground, and so it's getting tilted over. It's still a dangerous tornado. It's still picking up debris. It can still destroy houses, but this is getting towards the end of the life cycle of the tornado. And here we have one that we're basically saying is roping out. It's definitely getting stretched and pulled, and it's losing touch with the cloud that generated it. It still has a visible funnel that extends all the way to the ground, but this tornado is almost done. If we look at the damage patterns associated with tornadoes, we use the enhanced Fujita scale. Ted Fujita was a professor of meteorology at the University of Chicago, and he spent his career studying damage patterns. And he categorized them into this scale based upon the damage and not necessarily on the wind speed, although we do have rough wind speed categories that correspond to the Fujita scale. So an F1 tornado is capable of lifting shingles off roofs and denuding trees, moving other things around. The wind speeds are thought to be between about 80 and 117 miles per hour. In an F2 tornado, it will generally remove the roofs off of buildings and will leave the interior structure and the walls intact. This has wind speeds up to 160 miles an hour. An F3 tornado with wind speeds up to about 209 miles an hour will remove the roof and do significant interior damage to most structures. The F4 tornadoes that have wind speeds up to 260 miles an hour will essentially remove the roof and destroy the structure completely, but not remove all the debris. And an F5 tornado will basically obliterate even brick and cinder block buildings with wind speeds up to 317 miles an hour. I love this picture. It has a bathtub in the middle of this house, but I'm pretty sure that that bathtub probably came from a house a block or two away and just happened to end up in this debris field because everything from this house is gone. So here we have an aerial view of a relatively small tornado path. Can you see it? Can you see where the tornado passed through this green lush area? It's a brown area. So the tornado did in fact leave a path on the ground, and it shows one of the characteristics of tornadoes. Although tornadoes generally travel in one direction, they can meander about. And so this tornado is actually moving, obviously off towards the left at an angle, but it meandered to the right for a short period of time before it got back to its original track. And that's a common characteristic of tornadoes as they move. They generate lots of flying debris. I always love this one because it dates me, but this vinyl LP got accelerated probably to 200 miles an hour or more, and it's sitting embedded into a telephone pole. So if you think about what's dangerous about a tornado from a human perspective, it really is flying debris is one of the most dangerous things, where it can turn ordinary objects into lethal weapons. Being in a vehicle is extremely dangerous during a hurricane because these vehicles will get lofted into the air, and they can be lofted very high in a short period of time. So generally speaking, it's a good idea to not be in a vehicle if you get hit by a tornado, but you may use a vehicle to escape from a tornado if you have clear line of sight and you know exactly where the tornado is and what direction it's moving. So on the left, we had a truck who interacted with a tree. I think they both lost in this scenario. The truck is wrapped around the tree, and I can't imagine that tree surviving. That just shows you how strong the winds are inside these tornadoes. So just to reiterate, cars and trucks are a bad place to be in a tornado. So like I said, when it comes to tornadoes, the stronger the wider the tornado, the stronger it is, and the more dangerous it can be. And here's an example why. So we have 4 different size tornadoes. The one in the upper left, labeled A, is a relatively small tornado. It has air, a low pressure at the center, and air is flowing in towards the center and then ascending, much like the animation that we had. For B in the upper right, we have a vortex breakdown part where inside the middle of the tornado, we have a return flow which is coming down towards the low pressure at the center of the hurricane at the ground. this tornado is a little bit wider than the one labeled A, and it's going to have a little bit stronger wind speeds. Where things really start to take off and the tornadoes become a lot stronger and a lot more deadly is in the bottom left, where you have a central downdraft in the tornado that actually makes it all the way to the ground. So when that happens, the tornado will get wider very rapidly, and the wind speeds will increase quite a bit. And the secondary thing that'll happen when you get that central downdraft that reaches the surface is you now have wind that's going towards the tornado from inside and from outside the tornado, and it can actually generate what we call suction vortices on the periphery of the tornado. And these are literally tornadoes within the tornado, and they move around and rotate around the tornado, and they have the strongest winds inside the tornado. So the tornado on the bottom left may have wind speeds of 150 or 200 miles an hour, but inside the suction vortices, you're going to have wind speeds of 250 to 300 miles an hour. Here is a computer animation that actually shows a tornado with two suction vortices in it. And notice how they dance around, how they lift and come back down to the surface, and how they rotate around the main body of the tornado. There are some common myths associated with tornadoes. First of all, that highway overpasses are a safe place to seek shelter. That stems from a viral video that happened back in the mid-1990s. There's another myth that you should open windows if a tornado is approaching. That is a myth that stems back from the 1940s, when we didn't understand that the pressure of perturbation inside tornadoes was not large enough to cause buildings to explode, but the wind speeds were high enough to destroy those buildings. Myth number 3 is that tornadoes never strike big cities. That is not true. We've had a tornado go right through downtown Salt Lake City before. There's also been through downtown Houston and through downtown Atlanta. Myth number 4 is that tornadoes never strike the same place twice. No truth to that either. In the town that I grew up in Kansas, there was a furniture store outside of my town that got hit by a tornado 3 times in a 10-year period. I went back recently, and it's no longer a furniture store. They gave up. Other myths associated with tornadoes is that the southwest corner of a basement is the safest location in a house. Well, that presumes that the tornado is coming from the southwestern direction, and while that is often the case, it is not exclusively the case. Myth number 6, that mobile homes attract tornadoes. Well, they may not attract tornadoes, but they do attract news crews. And a lot of times they attract news crews because an F0 or an F1 tornado can do a lot of damage to mobile home park as opposed to your traditionally structured homes. Myth number 7, tornadoes can't occur in mountainous regions. Also not true. I've seen pictures of tornadoes in Rocky Mountain National Park in Colorado. And the last myth is that Doppler radar can provide advanced warning for all tornadoes. Well, that's not true, but Doppler radar can provide advanced warning for the largest and most deadly tornadoes, the F4s, F3s, F5s, that would most likely to kill people. So we use that Doppler radar system is the WSR-88D installation of radars within the contiguous U.S. They have very good coverage over most of the United States, and these are equipped with Doppler radar, which allow us to see the radial wind velocities. In areas where the Dopplers actually overlap, you can get the actual wind direction and speed as well. So we've seen this episode before, but this is the tornadic outbreak storm from May 4th of 1999 in Oklahoma City. On the left, we have the precipitation radar with the characteristic hook echo of the supercell. On the right, we have the Doppler radar. The Doppler radar, in this presentation, the red winds are moving towards the radar, and the radar is situated to the very right center, the little black circle. And the green is essentially air that is moving away from the radar system. At this particular point, the computer has identified a rotation, a green touching a red area there, and that can only occur if you happen to have rotation. And that identified that as a mesocyclone. That's not the tornado, but that's the rotating mesocyclone above the wall cloud. And it's been tracking it for some time. and it is forecasting where that mesocyclone is likely to go in the purple line. And it actually has been identified as a probable location for a tornado, which was then verified by spotters. Individual people that are trained at spotting severe weather are then able to verify that a tornado is in fact on the ground associated with this particular storm. This turned out to be an F5 tornado that moved through Oklahoma City and Moore, Oklahoma. This particular day spawned lots of different tornadoes. The National Weather Service counts each tornado as each segment of a tornado that is on the ground as a separate tornado, and the strength of the tornado is determined by the damage at each location. So in the center of this picture, we have an F5 tornado that moved through Oklahoma City, but it started off as a F3, F2, F1, and gradually intensified, reached a category 5, EF5 for a short period of time, weakened, and then turned back up to an EF5, and then eventually lifted off the ground. This particular storm spawned a total of 58 separate tornado damage paths, and they ranged from F0, F1s, all the way up to F5s. So for tornado safety, here's what you need to know. If you're in a car and you know where the tornado's at, drive at right angles away from it. You should be able to basically get out of the path of the tornado. If you're in a home and you have a tornado warning, go to the basement or an interior room in the house. And if no basement exists, then you can lay down in a bathtub and cover yourself up with a blanket, because you're really trying to avoid flying debris or things falling on top of you.